So I want to start today by suggesting something rather strange. I want to suggest to you that in a sample of pure water, quote unquote pure water, there is actually a small amount of particles other than H2O. And the reason is because H2O does a little bit of actual self-dissolving. A small fraction of the water molecules in any liquid sample of water are going to actually ionize. And when they do so, you're going to get a small amount of H plus and a small amount of OH minus hydroxide ions. Now, it's a very small amount. In fact, it works out mathematically that if you have 1 liter of H2O, you will end up with about 1 times 10 to the negative 7 moles of H plus. And it shouldn't be too surprising if you look at this equation that you'll end up with the exact same concentration of hydroxide ions. And the reason is because for every hydrogen ion that was produced, there was also a hydroxide ion produced. So a sample of pure water is in some sense not actually pure water. There's a small fraction of the water molecules that have ionized to produce H plus and to produce OH minus. Now it's a very small amount, right? 1 times 10 to the negative 7 is a pretty small number. But in a solution of water, we can confidently say that the concentration of H plus is equal to 1 times 10 to the negative 7 molar. And the concentration of OH minus is also equal to 1 times 10 to the negative 7 molar. Once we have that understanding, we can start to consider solutions that are not pure water. So I want you to imagine now, let's kind of leave our pure water alone for a few minutes, and let's imagine that we have a solution. I'm going to start off with a pure water solution, but we're going to add something to it. Imagine that we have a solution of pure water, so we know that everything we just said applies. We know that there is some hydrogen in there. We know that there is some hydroxide in there. And we know the initial concentrations in pure water would be 1 times 10 to the negative 7 for both. And I want you to imagine that to this solution, we add hydrochloric acid, HCl. Now, hydrochloric acid is highly soluble. As soon as it gets into the water, it's going to ionize. It's going to produce H plus, and it's going to produce OH minus. Now, it shouldn't be too surprising that if we go and look at this solution after we've added the HCl, we're going to find that the concentration of hydrogen ions has increased. Why has it increased? Because we added hydrochloric acid, it broke up, we introduced more hydrogen ions. That's a direct result of introducing HCl into the solution, that the hydrogen ion concentration goes up. What's less obvious is the effect on the hydroxide ions. Now you might think that adding HCl would have no effect on the hydroxide ions. Now HCl is highly soluble. So the moment we put it in the solution, we're going to have it dissolve into H plus and Cl minus. Now it should be fairly obvious that this is going to increase the amount of H plus in the solution, right? We added HCl. When we did that, we were adding hydrogen ions directly into the solution. So it shouldn't be too surprising that one of the consequences of adding HCl is an increase in the hydrogen ion concentration. What's less obvious is the effect on the hydroxide ion concentration. So you might intuitively think, and this is going to turn out to be wrong, but you might intuitively think that this would have no effect on the hydroxide ion concentration, that when you add HCl, you're adding hydrogen, but you're not adding hydroxide. So why would it change at all? Well, here's the thing. In this solution, there's already hydrogen and there's already hydroxide. Some of the hydrogen ions that you add are going to bump into hydroxide ions, and they're going to combine with those hydroxide ions and just make water. So there's this kind of strange situation where adding H plus results in a decrease of hydroxide concentration. So one way that I've explained this before is that hydrogen ions and hydroxide ions can't really coexist in large amounts. That if you add hydrogen ions, they're going to react with hydroxide ions and they're going to make water. And if you add hydroxide ions, they're going to combine with hydrogen ions and make water. And there's a limit to how much of each you can have. You can't really have a large amount of both. The higher the concentration of hydrogen goes, the lower the concentration of hydroxide has to be. And there's a mathematical relationship that I think will make this a little bit easier to understand. And it's maybe not obvious where I'm getting this from, but the concentration of hydrogen ions times the concentration of hydroxide ions always has to equal 1 times 10 to the negative 14. It comes from something called an equilibrium expression. It's a little bit beyond our scope for a Chem 1 course, but it is nonetheless a helpful thing, I think, for understanding this, because if you look at this equation, if this number times this number equals some constant, then it stands to reason that if one of these numbers goes up, the other one has to go down. That's the only way that they could always produce the same constant. If you notice, this equation was satisfied back in our pure water example. 1 times 10 to the negative 7 times 1 times 10 to the negative 7 would in fact give us 1 times 10 to the negative 14. So with all of that in mind, we can start to discuss the pH scale. So the pH scale is a system for measuring how much hydrogen and how much hydroxide there is in a solution. It's all relative amounts. Remember, we know that you cannot have really high concentrations of one. In fact, the more you have of one, the less you have of the other. So at one end of the pH scale, we can imagine a 0. And at the other end of the pH scale, we're going to imagine a 14. And I'll come back to the math behind it later on, but that's not the most important thing right now. The pH scale ranges from 0 to 14, with 7 being the midpoint. And the idea is that one end of the scale represents acidic aqueous solutions, and one end of the scale represents what we're going to call basic aqueous solutions. Now, an acidic aqueous solution is one where the hydrogen ion concentration is high and the hydroxide ion concentration is low. And a basic solution is exactly the opposite. A basic solution represents a situation where the hydrogen ion concentration is low and the hydroxide ion concentration is high. And again, you have to remember they can't both be high. You can't have a high concentration of hydrogen and a high concentration of hydroxide because they would just combine and make water. You also, conversely, you can't have a low concentration of both, or an especially low concentration of both. So this is a spectrum. This is a trade-off if you have an exactly equal amount, if the amount of hydrogen ions, concentration of hydrogen ions equals the concentration of hydroxide ions, then you're at a 7. Right? But anywhere other than 7, one is higher than the other. The further you get from 7, the more uneven the ratio of hydrogen to hydroxide becomes. So pH can be calculated. There is a formula for it. The pH of a solution is equal to the negative log of the concentration of hydrogen ions in that solution. So we can use our pure water example to prove it. We said earlier that in a sample of pure water, the concentration of H plus equals 1 times 10 to the negative 7. So if we plug into our formula and plug into our calculator, pH equals negative log of 1 times 10 to the negative 7. What we'll find, plug that into your calculator and double check it, is that the pH comes out to be 7. You could imagine a solution where the concentration of hydrogen, let's make it a lot higher, so a much higher concentration of hydrogen would be something like 1 times 10 to the negative 2, and our pH would be equal to the negative log of that number. And in this case, if you plug it into your calculator, the pH does come out to be 2. Plug it into your calculator. Resist the temptation, if you can, to just grab the exponent and make it a positive number and call it the pH. That's going to work if the base here is 1, exactly 1, but otherwise it's not going to really work. So you want to be able to do it with the negative log function on your calculator. You can reverse the math. So I know logarithmic algebra is not something you use every day, so I'm going to quickly give you the same equation. pH is the negative log of the hydrogen concentration. We can manipulate this equation a little bit and say that if you had to use it the other way, the concentration of hydrogen in a solution is equal to the number 10 raised to a power of the negative pH. If your logarithmic algebra is really good, then you probably already know that. But if your logarithmic algebra is a little bit rusty, don't blame me for that. That's the algebraic manipulation of the same equation. So these two equations are exactly equivalent to each other. The one on the left has got pH alone, and the one on the right has got the concentration of hydrogen ions alone. So just as an example, the pH of orange juice is about a 2.5. So if I wanted to know the hydrogen concentration of orange juice, then I would say, okay, H plus equals 10 to the negative 2.5. You're going to want to plug that into your calculator. And what I'm getting here for concentration of hydrogen ions is 3.1 times 10 to the negative 3. So I want to do one more application of this with you today. To do it, I want you to imagine that we are working with a 2.6 times 10 to the negative 4 molar HCl solution. Hydrochloric acid is what we call a strong acid, which means that when we dissolve it in water, it is going to dissolve completely. It's completely soluble. And at least at the concentrations that we're using, there's always a theoretical limit to solubility. But we're going to assume that this amount of HCl will dissolve easily in the water, which it will. If we dissolve 2.6 times 10 to the negative 4 moles per liter of it, then you can see one molecule of HCl gives us one hydrogen ion and one chloride ion. So we should expect that the concentration of H plus in the resulting solution is 2.6 times 10 to the negative 4. And we should be able from that to calculate the pH of this solution. So we know that the pH of the solution will be equal to the negative log of 2.6 times 10 to the negative 4. So we can plug that into your calculator. When I do that, I get a pH equal to 3.59. Okay, so far so good. But now we want to take that number, and really I want to take this number up here and use it to calculate the amount of hydroxide. So we know that for an aqueous solution, the concentration of H plus times the concentration of OH minus should equal 1 times 10 to the negative 14. Using that equation, we should be able to solve for the concentration of OH minus, which would be equal to 1 times 10 to the negative 14 divided by 2.6 times 10 to the negative 4. And what we're going to get is that the concentration of hydroxide ions is equal to 3.85 times 10 to the negative 11. So if you notice, our relationship up here has been very useful to us. We started off knowing how much hydrochloric acid was in there, but now we know the hydroxide concentration as well. There is also something called the POH. POH works just like pH, except it uses a different ion. So POH is equal to the negative log of the hydroxide ion concentration. So if you wanted to, you could calculate the POH here. You could take the negative log of 3.85 times 10 to the negative 11. And what you're going to get is that the POH equals 10.41. To tell you the truth, I probably, if you just asked me for the POH, I probably wouldn't get it that way because there's a really cool relationship here. The pH plus the POH have to always total up to 14. This comes out of the math, again, of the logarithmic scale, but we kind of have these two relationships here that are really the same relationship. There's the ion concentration relationship where the concentration of hydrogen times the concentration of hydroxide has to equal 1 times 10 to the negative 14. And then there's this second relationship that the pH plus the POH always has to equal 14. And they're not really two different relationships. They're the same thing mathematically. If one is true, the other is true.